Okay, let's sketch a graph using rules for increase, decrease, and concavity. So we're not looking for perfection, we're looking for somewhat accuracy. Let's do the first thing by doing increase. In order to find increase and decrease, you're going to take the derivative, which gives you critical points. So let me write that over here. It's going to be fun trying to fit this all in one screen. Probably not going to happen, but that's all right. Critical points are going to be found by taking the derivative. So you're going to bring that 4 down, and the 4 over here cancels each other out. So that leaves you with negative x cubed plus 2x, and then nothing. Set it equal to 0. Let's factor out a negative x. Yeah, let's factor out a negative x. When we factor out a negative x, that leaves us with x squared minus 2. Set these both equal to 0. So 0 is going to equal x and negative x, which means x equals 0. Sorry if I jumped ahead too fast. X squared minus 2 equals 0. Add 2 gives you this. Square root both sides. Don't forget to attach a plus or a negative over here. And so my critical points are going to be negative square root of 2, 0, and the square root of 2. So remember when I said about a minute ago, it's going to be hard putting all this on one screen? It ain't happening. But what I have right now is I have a critical points concavity, or not, I'm sorry, not concavity, critical points increase, decreasing starting point. So I'm going to make myself a sign chart, S-I-G-N, not S-I-N. We're going to put negative square root of 2 on there. We're going to put 0 on there. We're going to put positive square root of 2 on there. In order to find increase and decrease and where that happens, all right, I'm going to pick numbers that aren't exactly these guys but live on the interval. So I can pick like, I don't know, negative 5, negative 1, 1, and 5. I'm going to plug these into the derivative, which is this guy right here, do a little bit of math. If I get positive, that means it's increasing on that interval. If I get negative, that means it's decreasing on that interval. So let's take our y prime and plug it in. Y prime of negative 5. Let's try to do this mentally. All right, negative 5, there's my derivative. Negative 5 is going to be, negative 5 cubed is going to be negative 125. That negative cancels it out. So 125 minus 10 is going to be positive. So this is increasing here. If I take y prime of negative 1 and plug in negative 1, I get negative 1 to the third power, which is negative 1, times the negative 1, which is positive 1. But I'm going to add positive 1 to 2 times negative 1, which is negative 1. So this is negative. Again, if you're like, what happened? Just throw it in a calculator, buddy. Trust me on this one. Y prime of 1. Okay. Negative 1 cubed is negative 1 plus positive 2 is going to be positive. So I'll move that over there. Positive. And then if I plug in regular 5 into the derivative to see if it's positive or negative, I will get 5 cubed, which is 125. That negative out there is negative 125. Negative 125 plus 10 is still pretty negative, which means that's pretty decreasing. So this is what I know so far. This guy is increasing all the way up until negative square root of 2, whatever square root of 2 is, like 1 point something, 1.7, I believe. Maybe not, maybe 1.4. I'll ask Siri to help me out with that one. And then it starts decreasing. It hits an x of 0, so it hits the y-axis, starts increasing again, and at square root of 2, it starts decreasing again. So this is happening like that. But that's not good enough. Need more specifics than that. Need a lot more specifics than that. So what I'm going to do is I'm going to start my inflection points up here. I'll probably end up erasing that when all is said and done, but you know, we'll see. We'll see what I can fit on this one little screen. So to find the inflection points, I care about the second derivative. So the first derivative was negative x cubed plus 2x. So the second derivative has me bringing that 3 down and squaring it, negative 3x squared, and then getting rid of that x to make it plus 2, and I really hate this problem. Inflection points, set it equal to 0. Let's factor out a negative 3. No, let's not factor out a negative 3. Let's just leave it like that. Factoring out a negative 3 gets me nowhere. I could subtract 2. Negative 2 is equal to negative 3 over x squared. Divide everything by negative 3. Divide everything by negative 3. I get 2/3 equals x squared. Square root both sides, positive or negative, and my inflection points exist at the square root of, you know what, I forgot to write out square root. My inflection points exist at negative square root of 2/3 and positive square root of 2/3, like that. So I'm going to make another sine table, but this time this is going to be for concavity. So let me put my concavity info right here. All right, I have negative square root of 2/3 and positive square root of 2/3. Now, the square root of 2/3 is, I know, somewhere in between 0 and 1. So again, I need to choose numbers that live in between these intervals, but not exactly on those intervals. So I'll choose 0, I'll choose negative 1, and I'll choose positive 1. So when I find the y double prime of that number, it'll tell me if it's positive or negative. If it's positive, it's concave up. If it's negative, it's concave down. So y prime of negative 1, if I plug in negative 1 to y double prime, I'm going to get negative 3 times negative 1 squared. So negative 3 times 1, negative 3 plus 2 is negative. So right here we have concave down. If I plug in 0 for y double prime, I get 0 plus 2, which is positive, concave up. And if I plug in regular 1 to y double prime, so y double prime of regular 1, I get literally the exact same as I get over here. So I get negative, which makes that concave down. All right, time to sketch. Now, again, the purpose of sketching is you're not looking for perfection. You're looking for like an accurate representation of what this picture looks like. So what's the lightest color that I can use on this thing? Like a nice yellow. Let's get a nice yellow up in here, like a gold. All right. So there's my coordinate plane that is awfully drawn. You can barely see it. The critical points and the inflection points are what really matter. Okay, so I care about the square root of negative 2. I care about the square root of 2/3, the negative square root of 2/3. I care about 0. I care about the positive square root of 2/3. And I care about positive square root of 2. And I think I've hit everything. Negative root 2, negative, I got it, 0's there, I got it. Now let's do some drawing. I increase, I'm increasing until I hit negative square root of negative 2. So let's draw something that's increasing. Once I hit negative 2, I begin decreasing until I hit 2/3. Once I hit 2/3, I start going concave up. So right now, you can see that negative 2/3 to the left is concave down. But once I hit negative 2/3, I start concave upping until I hit 0. Once I hit 0, my decrease becomes an increase and continues that trend until I hit negative square root of 2/3, where I become concave down again. Once I hit the square root of 2, my increase becomes a decrease, and so I get some kind of weird thing that looks like that. All right. Again, this is a sketch. This is not perfection. If I wanted perfection, then I would take all of these numbers, plug them into the original function, and get specific points. I could have done that, but I didn't. You know why? Because I have one screen here and I don't have all the time in the world. And I'm sure I have a video somewhere on the internet that involves me doing this. So, go find it and like and subscribe while you're at it. All right? That's that. Bye.